Hello, my name is Burak Kantarsi. I'm an associate professor at the University of Ottawa and the founding director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa. Today I'll be presenting our paper entitled Region-Aware Pegging and Deep Learning-Based Fake Task Detection in Mobile Crowd Sensing Platforms. Let me quickly switch to the agenda and the introduction after that. So I'll give you a brief introduction of mobile crowd sensing systems and their vulnerabilities. And after that, I'll talk about the works that address the problem that we aim to address in this paper. And then I'll talk about our proposal, how we are trying to address the fake task detections in mobile crowd sensing system. And then I'll present you our performance evaluation results, and then I'll conclude my talk and provide a few future directions in this study. So this is one of several vulnerabilities of this system, which is the fake task submissions. So we have worked on other challenges in mobile crowd sensing system, including data poisoning, including fake data submissions, and including the issues in incentivizing the users to participate in this crowd sensing system. Well, this one is a specific case where we receive fake task submissions or illegitimate task submissions to the mobile crowd sensing platform. So what does that mean? Well, not all of the tasks are legitimate, the tasks generated by the end users to recruit participants. And very recently, in June of this year, 2020, in ICC, we presented a deep leaf network-based detection of the fake tasks in mobile crowd sensing environments. So the deep leaf network-based solution that I will be also using here in this talk, I will be referring to that. The configuration of the deep leaf network that I'll be talking here adopts the architecture that was presented here in this paper. We have also worked on how those tasks can be submitted and how they can be disguised in the mobile crowd sensing environments. That was actually one of the topics we also studied, and we modeled these tasks to assist in the research for detection of these tasks. So this is actually one of our very recent works, empowering self-organized feature maps for AI-enabled modeling of fake task submissions to mobile crowd sensing platforms, which has been published in IEEE Internet of Things Journal. And of course, an improved version of this has been published in a locally reconfigurable self-organizing feature map for high-impact malicious task submissions in mobile crowd sensing, which has been published in Elsevier Internet of Things Journal. So if you're interested in how these threats are being modeled and introduced into the mobile crowd sensing system in a way such that they disguise themselves among the other tasks submitted to the system, well, these two papers are actually good resources for that, good sources for that, sorry. Now, the first thing, I was talking about the region feature, how that region feature is being extracted here by these models that we're going to be using to detect the fake tasks. The first thing we do here is, okay, this is actually, this is being done on the training set. Okay, this has nothing to do with the test set, of course, because the region feature is extracted, obtaining the regions actually is done on the training set. So what we do is we get the fake tasks at the beginning and we cluster them into K predetermined number of clusters, okay? And once we have these clusters, we get the centroids of these clusters, and we assign those centroids as the initial centroids of the k-means algorithm to cluster the entire tasks that include the fake tasks and the legitimate tasks. And then we obtain a map, a region map like this. So these are these red points are the tasks that are fake tasks in those regions. Okay, so this is just an example, and the region information is provided as an additional input to the detection model. And how the detection model works? Well, we have the mobile CrowdSensing platform here that generates the tasks that can be either fake tasks or legitimate tasks. Now, the region feature is being extracted, and then after that, well, principal component analysis runs to map the input dimensions onto lower dimensions, and then borderline smooth is being used here to address the imbalance problem, because majority of the tasks that are submitted into the mobile CrowdSensing platform consists of the legitimate tasks. So borderline smooth is to oversample on this data set to address the imbalance problem. And then there's the standardization step here. And there's a typo here, sorry about this. And after that, after the pre-processing step, there's the testing and training steps, where we can have either our deep leaf network or the ensemble solution here. I'm going to be talking about the relative performance of bagging-based detection compared to the deep leaf network-based detection. But the output of these machine learning algorithms will give us the legitimate or fake predictions for the crowd sensing tasks in this environment. Now, we evaluate the performance of the system in terms of various metrics. The first metric is, of course, the detection performance. And as you can see here, regardless of the region, inclusion of the region feature, bagging-based detection always outperforms the deep leaf network-based detection. And this deep leaf network architecture, this is actually the architecture that we used. That's the configuration we used in our previous study, which gave us the best results there, because we did investigate how we could configure the deep leaf network to be able to detect these fake tasks in our previous study. Now, what we see here is, okay, if the region information is included here, we can have a slight improvement in the performance of the deep leaf network, a slight improvement in terms of the precision and also recall, F1 score, accuracy. The G-mean performance is also improved a little bit, but these improvements are actually slight improvements, I would say, for bagging. Well, the improvement is not much visible here, but the G-mean performance is very slightly decreased. So better not to include the region information here in the detection process. We can just go with the bagging and DBN as is. But since there's a slight improvement in DBN performance, we also compare bagging-based detection to DBN-based detection with the region feature information. The second performance evaluation we perform here is the energy saving. As I said, if we detect the fake tasks, well, they won't undergo any processing, and we won't need to recruit additional participants for those tasks. So we're going to be saving that energy. Otherwise, that energy would have been drained from those participant devices. And in this figure, as we can see, well, these are the legitimate tasks, and the rest of the slice this is under bagging, and this is under deep leaf network. So here, these are the legitimate tasks, and the rest of this pie chart consists of the fake tasks. So the fake tasks that we are able to detect, this is what we assume the saved energy, okay? And the saved energy under DBN is here. And as you can see here, the saved energy under bagging is more than the energy saved under the deep leaf network. through the detection of the fake tasks. Now, how does this translate into the recruits? So this is the recruits or the recruited participants for the fake tasks. Well, and this is the total recruited participants. Well, what we need to check here is what is the impacted population here out of the entire recruits, which we call the impacted recruits. So as you can see here, if you don't have any AI-based detection mechanism here, well, more than 10% of your recruits are going to be impacted here, which means that they're going to be recruited for at least one fake task. Well, for if you go with begging, it's 0.25%. If you go with a DBM-based detection, it's slightly higher than this. 0.71% of your population is going to be, of your recruited population is going to be impacted. And how about the entire participants? Well, because a participant is not necessarily to be recruited. Well, this is the total, the number of total participants. Sorry, this is the total number of participants, and this is the participants that are candidates for the fake tasks. And this is actually the impact on these participants. So the DBN, impact under the DBN is close to 1%, but the impact under the begging based approach is way less than 1%. Well, if you go with begging based detection, well, the performance, detection performance of the deep leaf network that we introduced before is going to be improved regardless of the usage of the region feature. And if you go with the region feature, the geometric mean of the sensitivity and specificity, this actually is improved under the deep leaf network from 96% to 97%. But for begging, there's almost no changes. There's a very, very slight drop here. And the machine learning models, they also improve the platform's energy savings. If you go with begging, the energy saving here is energy saving due to the elimination of the fake tasks is more than 12%. Whereas if you go with a deep leaf network-based solution, your energy saving is at the order of 11.8%. So another improvement over the deep leaf network in terms of energy consumption. And we also reduce the recruited population for the fake tasks. And we also prevent most of the participants to be considered, prevent most of the participants from being considered for fake tasks. And the task completion rate is also slightly reduced here when begging is compared to a situation where we don't eliminate any tasks. So it's less than 1%, as you can see here, 0.57%. But under the deep leaf network, it's more than 1%, 105% is the influence rate as we introduced here. And the next step, or the future directions in this work, is going to be addressing this influence rate, which is, again, as I said, the side effect of the detection mechanism, which is actually an outcome or a consequence of false decisions. So we are now working on other machine learning based solutions now to address the false detections or false decisions made in this work, to be able to address or to be able to catch those missed points in this work as well. Well, that concludes my presentation, my talk, and thank you very much for listening, for following. If you're interested in either this work or other relevant works of our lab, you can always reach us here. This is our research lab's address, nexconlab.academy. We'll be happy to provide you with more information. Thank you very much.